Hey everybody! Today what I wanted to do was take a look at the problems that we did yesterday, the physics applications. We worked them out algebraically, and I wanted to show you how we might do that with a graphing calculator and approximate the answers. So you don't need to take notes on this necessarily, but you do need to be able to go through these kinds of steps yourself with your own graphing calculator. And when we have our test, you will have a problem that you're using your graphing calculator to solve, kind of similar to this. Okay, so we have the football that's thrown upward with an initial velocity of 60 feet per second from a height of 6 feet. So remember that that gave us the equation S of t equals negative 16t squared plus 60t plus 6. That was our position equation, and our velocity equation was v of t equals negative 32t plus 60. So what we're going to do is graph the position equation. So we go to y equals, clear out anything that's there, and type in this equation, negative 16x squared plus 60x plus 6. Now, if we remember the values that we got when we did the problem yesterday, it can help us to establish our window dimensions. I don't happen to remember, and in the event that you're doing a problem that you didn't already do, what you want to do is think about what would be reasonable numbers for time in this kind of situation. So it's probably only going to take a matter of a few seconds for the football to come back down to the ground. So let's go to window, and let's say that our minimum value of x is negative 2, not because there's a negative time, but because if we use a negative x value, then it will show us the y-axis. And then let's say our maximum is 10, so that would be 10 seconds. We can adjust this if we don't like these numbers once we look at the graph. Okay, the y values represent the height of the football. I'm going to go ahead with negative 10. We know it's not going down underground, but having a negative there will show us the x-axis, so that's helpful. And then I don't really remember what the maximum height was, so I'm just going to leave this at 100. That sounds like a good thing to try. And then I'm going to press graph. So there's the path of the football. In other words, there's the height as a function of time. So for part A, when will it reach the peak of its flight? We're looking for the x-coordinate of the vertex. So we press second trace to take us into the calculate menu. And we go to number 4, maximum, because the vertex is at the maximum this time. Press enter. Then we take the cursor to the left of the maximum, because it's asking us for a left bound. Press enter. And then to the right of the maximum, press enter, and then in between, and press enter. So we actually get approximate answers for parts A and B this time. For part A, we have approximately 1.9 if we're rounding to the nearest tenth. You just have to follow whatever rounding directions you're given in the problem, if you're given any. You might remember that the exact answer from yesterday was 1.875 because it was 1 7/8. So you can see that the calculator wasn't actually able to find the exact answer. It just used a method to approximate the answer. Still, it's a very good approximation. So 1.9 seconds, and then the maximum height is the y-coordinate of the point, so that would be 62 1/4 feet. And hopefully that sounds familiar because that's the answer we got yesterday when we did this one on paper. Okay, for part C, when will it be 20 feet high? So I'm going to go back into the y equals menu and go down to y2, and I'm going to let y2 equals 20. So that's going to be a horizontal line at a height of 20. Then we press graph again, and we see that horizontal line. So we're looking for these 2 points of intersection, and we're looking for their x-coordinates to have the time. So we press second trace to take us into the calculate menu. We choose number 5, intersect. We put the cursor on the first curve and press enter. Put the cursor on the second curve and press enter. And then we move the cursor close to the intersection point we're interested in and press enter. I'm just going to do this one on the right first because that's where my cursor happens to be. So notice that we get x equals 3.5. Okay, now we repeat the process for the other intersection point. So second trace to take us into calc. Choose number 5 for intersect. Cursor's on the first curve, press enter. Cursor's on the second curve, press enter. And then move the cursor closer to that other intersection point and press enter. And that one is 0.25. So you might remember that we got 1/4 and we got 7/2 when we did it on paper yesterday, and these are the same answers. Okay, for part D, we can do a very similar thing, but instead of y equals 20, we can use y equals 80 and graph that line. And you see the line is above the path of the football because it doesn't reach that height. It only goes up to 62 1/4 feet. So we'll just say none. Okay, for part E, when will it hit the ground? We're looking for the point that we call a 0 or a root, the point where it hits the x-axis. So let's press second, trace to take us into calc, and let's choose number 2, 0. And then it wants a left bound, so move your cursor to the left of the 0, press enter. And then it wants a right bound, so move your cursor to the right of the 0, press enter. And then it wants a guess, so move in between and press enter. Notice the y-coordinate is -1 e -11, and remember that means in scientific notation -1 times 10 to the -11th, and that's -0.000000000001. So that's essentially 0, and the x-coordinate rounded to the nearest tenth is 3.8, so it reaches the ground at about 3.8 seconds. Okay, now we're on part F, and part F is asking about velocity. So we're done with the position equation, so I'm going to clear it, clear the other one as well, and let's type in the velocity, -32t, or x, plus 60. So the window that we need for this is going to be different from the window we needed for position, because the velocity values are not necessarily the same as the position values. The times might be the same. Let me go ahead and just press graph and see how we do with this window. It's not really so good. It shows us the positive velocities, but we need to see the negative velocities down here. So let's adjust the window and let's make our y values go from -100 to 100. Okay, so now we see the positive velocities and we see the negative velocities. Remember, it has a positive velocity when it's going up and a negative velocity when it's going down. So to find the velocity at 1 second, what we can do is press trace and then type in the letter, actually it's a number, excuse me, the number 1. I should have watched more Sesame Street when I was little. And press enter, and you'll see the cursor moves to the point 128. So that's telling us that the velocity is 28 feet per second at time 1. And then we can repeat that process for part G. What's the velocity at 3 seconds? Press trace, type in a 3, press enter, and we have -36 as the velocity at that time, so -36 feet per second. Okay, let's go through problem number 2. So this is the one with the arrow that was fired, and we're again going to use a calculator. What we want is our position equation, S of t equals -4.9t squared plus 30t minus 15. 30 is the initial velocity. It was on its way up, so it's positive. And -15 because we're down below the ground surface, down at the bottom of the well. And the velocity was v of t equals -9.8t plus 30. So here's the calculator again. Go into y equals and clear what was there. And let's type in our velocity equation. And then for times, it's probably reasonable to keep the times we were using for the last problem. And then in terms of heights, I don't exactly remember how high the arrow went yesterday, so let's just go with -10 to 100, and we can adjust it if that's not a good set of values. Seems like it was a little high, so if you want to, you can go back down to like y max of 50, let's say, just so that your graph fills up more of the screen. It's better if your graph fills up the majority of the screen. We don't even need our x values to go that far. We could go to 8, let's say, and then it does an even better job of filling up the majority of the screen. When will it reach the surface? So we're looking for the zeros. we're looking for the times when the graph is at a height of 0. So just like we did for the last problem, second trace to take us into the Calculate menu, choose number 2, 0. Move the cursor to the left of the 0. I'm going to do the one on the left first. Press enter, and then to the right, press enter, and then in between. And we get approximately 0.5. And then we do it again for the other one, second trace. Choose number 2, 0. Move the cursor to the left of the 0. Or type in a number if you don't want to wait on the cursor. Press enter, and then move the cursor to the right of the number. Press enter, and then in between and press enter. And we get approximately 5.6. And those numbers sound familiar based on what we did yesterday. Part B, when will it be 30 meters above the surface? So let's go back to y equals and go to y2, and let's type the line y equals 30. Press graph. And there we see right there, it's reaching a height of 30 at 2 different times. So we go into our Calculate menu, we choose number 5, intersect. Put the cursor on the blue curve, yes. Cursor on the red curve, yes. And then move the cursor closer to the first intersection point, press enter, and we get approximately 2.6. And then we do it again, into the Calculate menu, choose intersect. Cursor on the blue curve, yes, enter. Cursor on the red curve, yes, enter. Move it over closer to that other intersection point, and we get approximately 3.5. Okay, for part C, we're looking for the velocity at 2 seconds. So we go into the y equals menu. Actually, I'm going to do part D first, because it's going to use the, it could, if we want it to, use the equation or the graph for position, because we know the first time the velocity is at 0 is when the object is at the top. So let's go ahead and find that maximum. Into the Calculate menu, choose number 4, maximum. Go to the left of it, press enter. Go to the right of it, press enter, and then in between, press enter. And we get approximately 3.1 seconds. And the height there is 30.9. So to answer the question, 30.9 meters approximately. Now there is another way we could do that part. So we could take our velocity and set it equal to 0. 0 equals negative 9.8 t plus 30. Solve for t. And then we could take that time, and once we have that time, we could simplify it. We could then put it into our position equation. So there's actually a few different ways to get that part. Now let's go back to part C. What's the velocity at 2 seconds? So I'm going to clear out my equation for position and type in my equation for velocity and change my window. Let's go with maybe negative 50 to 50 for the y values. That way we see the positives and the negatives. And at time 2, I'm going to press trace, type in a 2, press enter, and there we have the point, and it has a y coordinate of 10.4. So the velocity was 10.4 meters per second at that moment. Okay, so that takes us through both of these problems, approximating our answers using the graphing calculator. Okay, for today's assignment, I thought we would do some variety problems. So there's a mixed problem solving page in your book, numbers 1 through 9, and there's all different kinds of problems. Some of them you might use a graphing calculator to solve. Some of them you're probably going to do just by hand. And I want to talk about number 3 with you and just do it together. So number 3 has to do with quadratic regression. And if you remember, the day we learned a lesson that involved quadratic regression, I told you you didn't have to write it down and I wasn't going to test you on it. It's still a great problem, so I still want us to do this problem just for the experience. So page 316, number 3, open your book, take a look, and we're going to do this on the calculator. So we're given some data about the year since 1998 and the price of a VCR. So not only is this a math problem, but it's a history problem. Do any of you actually have a VCR in your house? Does it work? That would be pretty incredible. My wedding video is on a videotape, so I won't be watching that anytime soon, unless I get it converted to another format. It was the early 90s. I had a perm, big bangs. It was great. Do you know what a perm is? Permanent? Where you get your hair chemically altered so that it's curly. So, here we go. We're going to enter the data into the calculator. So we go to Stat, and then we go to Edit, and I'm going to clear the numbers that are in the lists. You can also just clear the memory of your calculator to make it easier. And then we're typing in the numbers. So for X, we have 0, 1, 2, 3, 4, and 5. That's list 1. Those are the years since 1998. And then for list 2, we have the price of the VCR. So what's happening is the price started out high because it was new technology, and often new technology costs a lot, and then the price went down because over time it wasn't new technology anymore, maybe the demand was lower. So what we can do once we have the data in the calculator is find the quadratic model. So we press Stat, go over to Calculate, and go down to number 5, Quadratic Regression. Press Enter, and then Enter, Enter. Now when it comes to storing, I'm going to store it in my Y1. So I'm going to press Vars, over to YVars, choose Function, and choose Y1. And now I'm going to calculate. So there we have the values of A, B, and C that would go in the equation. It's quadratic, apparently because those values were not going down in a linear way, they were going down in a more curvy way that would be replicated by a parabola. So if we look at our y equals menu, we see that equation has been pasted in. So now we're going to graph. So for part B, what I want to do is go into my stat plot menu, second y equals, turn on the first stat plot. It's a scatter plot. And then I'm going to go to zoom and choose zoom 9, which is going to set a good window for me based on the scatter plot data. So there you see the scatter plot as well as the curve. Now, the final part of the problem asks you this question. Do you think this model will give a good estimate of the price of a VCR in the year 2010? Well, what if I change my window? 2010 would be 12 years past 1998. So I'm going to actually go to, let's go to 25. We might have to change our Y maximum. I'm going to do that as well. Maybe I'll make that something like 300. Okay, so let's press Trace, and then the down arrow to take us to the curve, and I'm going to type in a 12. So 12 years past 1998 is the year 2010. Do you think the VCR would have gone back up to $267.71? I don't think so. Even though we could model the equation initially with a quadratic curve as it sloped down, it doesn't make sense that it would slope back up. I mean, maybe someday if you had like a really rare item and it was in high demand because it was rare, was valuable for that reason, the price might go back up. But this lesson that we're learning here is that a model is really only good for a short period of time. You can't necessarily use the model to make predictions, or remember the word extrapolations, that are very far beyond. In fact, what about the year, well, what year is it now? 2020, so that would be 22. What if X was 22? I haven't even gone far enough with my Y values to be able to see that. I might have to go up to like 1,000. So let's press Trace, 22. Oops, I'm not in my graph, am I? Trace, 22. Oh, what am I doing? Ah, I know. I have to press Trace. Then I need to use my down arrow to get back to the right curve. Now I can type in a 22. Okay, would it really cost $1,178.39 to buy that VCR today? Probably not. Okay, so then you can go back and do the rest of page 316. Thanks, everybody.